All right, this is the video guide going over the ideal gas law. Basically, an ideal gas is a gas that follows the gas laws at all conditions of pressure and temperature, and it's what you need to determine the number of moles. So if you see anything dealing with like moles or a specific mass or something of a gas, you're generally going to be using this ideal gas law. What you need to be aware of is that real gases deviate from ideal behavior at very low temperatures and high pressures. Okay, and so what we're talking about with this ideal behavior, okay, that's going back to the kinetic molecular theory, where the particles are small and they spread out, they move around just in straight lines until they bounce off something. They're perfectly elastic, and usually gases will follow that kinetic molecular theory, but there are times when they deviate from it. That's when, if the temperature is really cold, really low, and they don't move around a bunch, then they don't really behave ideally. Or if you have tremendous pressure on them, if you're pushing on them, just squeezing them together, they can't expand and fill the container. But usually they are going to follow, all the premises of that kinetic molecular theory. All right, so what I want you guys to notice here is the formula for the ideal gas law. PV equals nRT. Okay, pressure times volume. N is the number of moles. Okay, R is this new thing. R is what's called the ideal gas constant. Now, what you're going to notice, here are 3 examples. There are some others on that gas law cheat sheet I gave you, but basically you might think, well, if this is a constant, why are there different values? Well, if you look at them, so this one's atmosphere liter per mole Kelvin. This one's kilopascal liter per mole Kelvin, millimeters of mercury liters per mole Kelvin. Everything is the exact same with the exception of the pressure units. And so that's the only thing that's really going to change on these ideal gas law problems is basically what pressure unit, and make certain you're using the correct value for R. And that's it, but it's basically just like doing any of the others. I'll run you through a couple. So this is an example. It says I have an unknown quantity of gas at a pressure of 121.6 kilopascals, volume is 31 liters, temperature is 87 Celsius. I want to know how many moles I have. So, because it's asking moles, we need the formula of moles in it. PV equals nRT, pressure, volume, number of moles, gas constant, temp. Then all you do is plug in what you know. Pressure, 121.6 kPa, kilopascals. Volume, it says, is 31 liters. The number of moles is what we're solving for. That's X. Because this pressure is in kilopascals, we want to use the kilopascal value for R. And so you go back and look at it. It's this one, the 8.31, okay? So we're going to say 8.31 kilopascal liter per mole Kelvin. And then temperature is 87 Celsius. So you have to take 87 plus 273 because it has to be Kelvin. When you do so, that should be 360 K. Okay. Now all I need to do is solve for X. So I need to get it by itself. So basically I'm going to divide 8.31 kPa liter per mole Kelvin. And then 360 Kelvin. Okay. Now what you're going to notice, liters cancel. Kilopascals cancel. Kelvin cancels. We're left with moles, which is what we wanted. So I'm going to take 121.6 times 31 divided by 8.31 divided by 360. And when you do that, you get 1.2600, yada, yada, yada. Okay. We're limited to 2 sig figs because of 31. 1.3 moles. That is your answer, rounded with the appropriate number of sig figs. Let's do one more. Okay, it says I have 7.7 moles of gas at a pressure of 0.09 atmospheres, temperature 56 Celsius. I want to know the volume of the container. Well, once again, we're using the same formula, PV equals nRT. This time we're solving for volume. That's okay. So we know the pressure, 0.09 atms. The volume we do not know. The number of moles was given, 7.7 moles of gas. And R, if we're using atmospheres, you got to go back and look at 0.0821 atmosphere liter per mole Kelvin. And then 56 plus 273 should be 329 Kelvin. All I need to do is solve for x. I need to get by itself, so I'm going to divide by 0.09 atmospheres. This cancels. Moles cancel. Atmospheres cancel. Kelvin cancels. I'm left with liters. I'm going to take 7.7 times 0.0821 times 329 divided by 0.09. When I do so, your calculator is going to poop out 2,310.9. However, I'm limited to 1 sig fig because of that number. The answer should be 2,000 liters is your answer. Okay, I'm going to give you guys an opportunity to practice these, but it's not bad. It's no different from the others. It's just an equality where you know all the values except for one. You have to choose the correct R value, insert it into the formula, and solve for X. That's it. All right, I'll give you some to practice.